Greek philosopher Heraclitus said, "There is nothing permanent except change." And there's a force behind every change. A force is a change agent. This video is about the 4 fundamental forces of nature. A custom-built demo device will help explain them. Let's get started. Forces rule our lives. Pulling, pushing, accelerating are among the 20 forces shown here. Regardless of what names we use, there are only 4 forces. All others are really just one of these 4 in disguise. First, an overview of the forces. Gravity. Every mass in the universe is attracted to every other mass in the universe. Gravity has an infinite range. The forces associated with electromagnetism can attract or repel over any distance. Magnets, electricity, radio waves, Wi-Fi, and even light are manifestations of electromagnetic force fields. The weak nuclear force is an interaction responsible for a form of radioactivity. It operates at the atomic level. Finally, the big daddy of forces, the strong nuclear interaction. It's the glue of the atomic nucleus. It's a multi-acting force responsible for the structure of protons and neutrons and holds them tightly together inside the nucleus. This demo device will help explain the 4 forces. Let's start with gravity. No big surprises here, since we balance against it all day long. You may have heard that space is really described in 4 dimensions, because time is the 4th dimension. This means that we live in 4D space-time, not 3D space. This brass ball falls in 4D space-time. But what does this really mean? First, Einstein went beyond Newton's what by explaining the how of gravity. So we need Einstein's help to dig deeper. If this makes you queasy, skip ahead about a minute. Physicist John Wheeler famously said, "Einstein's general theory of relativity can be summed up in just 12 words. Space-time tells matter how to move. Matter tells space-time how to curve." What did he mean? Our Earth puts a huge deep well in space-time, and the motion of nearby objects is affected by the curve of space-time. Mass warps the geometry of the surrounding space-time. The curve has been accurately measured by astronomers. Strangely, traveling through time causes us to feel acceleration, like the pushing force on the seat of your pants when riding a roller coaster, but without getting dizzy. Moving along curved space-time feels like gravity to us. This analogy of bent 3D space falls short of a full explanation, but we can't easily visualize 4D space-time, so an analogy is all we have. One other thing. Gravity is the weakest of the 4 forces. This may seem odd because the Earth is so massive, we feel its pull. No one ever said the theory of relativity was easy to understand, and it doesn't answer every question physicists have, but it's the best explanation we have for how gravity makes apples fall. Here's a steel ball, and here is an electromagnet. The magnet is energized by flipping the switch on and off and applying electricity to it. Energizing now. You see it's attracting the ball. It's holding it in place. When the switch is off, the ball is free to move. Now, I love the feeling that the field gives me when it's on. It's like fighting me to hold the ball. Between the ball and the magnet is a static magnetic field. This tiny gap here is where all the action occurs. But what is that action? Imagining what's happening here. Remarkably, light and radio waves are examples of propagating electromagnetic fields. Now here's the amazing part. A light beam, say from the sun, is described as a stream of particles of energy called photons, and as an electromagnetic wave at the same time. No one understands everything about the dual makeup of light. There are still some puzzling mysteries at the quantum level. So between this gap, here, photons, more correctly called virtual photons in this confined space, are essential for creating the force that attracts the steel ball. This demo does not show the full nature of the force, just one aspect. Not demonstrated is the force's electrostatic nature, where charged particles like electrons and protons attract or repel. Electricity and magnetism are essentially two aspects of the same thing. Why? Because a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Indeed, this force is complex. This is not child's play, and it took physicists like Ørsted, Maxwell, Einstein, and Richard Feynman, and others more than 200 years to uncover the secrets of electromagnetism. We move to the third force in this demo. This is the so-called weak interaction. Here is a vial of radioactive tritium gas. You can see it a little bit in here, even at this angle. There's a green glow to it. This demo is safe since the radiation level is very low. Tritium is an isotope of hydrogen. Its nucleus has 2 neutrons and 1 proton, whereas hydrogen has only 1 proton. It'll take about 12 years for half of the tritium gas in this vial to radioactively decay into stable helium. This simplified image shows 1 neutron of tritium being converted into 1 proton, an electron, and some energy not shown here. Importantly, the newly created electron is emitted from the nucleus. The new 2-proton, 1-neutron nucleus is a stable helium atom. The weak interaction transformed tritium into helium. Inside the vial, emitted electrons strike the phosphorus-coated glass, and a dim green light is emitted. Let's do a close-up of the vial to see the light. The low level of radioactivity generates dim green light. Bottom line, this is a good example of the weak force in action. This process is crucial for the sun to generate its light and heat. Finally, the strong force. It's often called the glue of the nucleus. This force confines subatomic particles inside the nucleus. This demo will show only one aspect of the strong force, the confinement of protons inside the nucleus. This force is multi-layered and does other important actions inside the nucleus, but it's not covered here. Let's use lithium's nucleus as an example. It has 3 protons and 3 neutrons. Protons have a positive charge and repel each other due to the electrostatic field. That's force number 2, which we just discussed. But without some added force, the nucleus would fly apart. The strong interaction comes to the rescue by providing a counteracting force to stabilize the nucleus. Push is balanced against pull. The force also keeps the neutrons from wandering off too. They stay confined. Now, this demo uses 2 magnets and a spring to illustrate the strong force. The 2 magnets are aligned in repelling opposition. These represent the 2 protons. The spring represents the attracting force, the strong force. The 2 forces balance perfectly to create an equilibrium. As the photon is a force carrier for electromagnetism, the aptly named gluon is the force carrier particle for the strong force. Let's do the demo here. We start with no spring, and we see that the two protons want to repel each other, and they would get as far away as they can before the force falls off. Now if we attach, using the spring, which represents the strong force, if we attach this, now we have a balance where the spring, represented by the, again, representing the strong force, is in equilibrium with the electrostatic force to push the two protons apart. So this is what's happening inside the nucleus. We have a beautiful equilibrium where this pulling apart is balanced by this pulling together to create a stable nucleus. This is a glue that we can't live without. Be thankful for the gluon. That completes the demo. Next time you go for a walk, maybe with your dog, look around and appreciate how awesome the four forces are. The strong interaction for atomic stability, the weak interaction to initiate nuclear reactions in our sun and stars, gravity to keep us from floating off, and electromagnetism for just about everything else we call a force. The amazing, powerful theory of quantum mechanics describes all forces of nature except gravity. In closing, you may enjoy learning about fine-tuning in physics. What is fine-tuning? There are roughly 25 fundamental constants of nature. These govern the composition of all matter and their interactions. The strength values of the forces are just 4 of these 25 constants. But what if any or all of the 25 constants had different values or magnitudes? Should we care? What would happen if, say, the force of gravity was stronger by 5%? Why are the values precisely what they are? To learn more, check out this website. It's a game-like simulator that allows adjustment of 6 fundamental constants. As you tune in each one, you are also tuning in an AM radio, complete with 20 channels of programming. It's a fun way to learn more about physics.